In order to execute the project assignment and its corresponding steps, I decided to use Microsoft Excel as the tool to create the model. Um, so my approach was first to understand the problem and the expected outcome, and then I decided to use um, the multiple linear regression approach for my model. And in order to do that, I just added the tool of the analysis tool pack to my work sheet in Excel. And then um, I decided to examine more in detail the original data set from the project. So, understanding what we wanted to accomplish, I decided to use the first four columns as the features for this model that you can see here in blue. And then I decided to uh, use the final one as the target of our model. So the first four columns are the ambient temperature, the ambient pressure, vacuum, and relative humidity, and then in green you can see the um, um, electric energy output with the acronym PE. At first, I had to do some formatting for the data set because of my local configuration. And then um, I decided to split this data set using the 80% of the first columns for training my model, meaning that I use until the row number 7,654 as the training data set. And then the rest of the data set, I split it in two equal parts. One to validate and compare to the two different models, and the final one to evaluate the final model selection. So the other thing that I did was to select the output metric to evaluate the performance of the model. Um, the one that I selected was the coefficient of determination R squared that you can see here as R2. But I also added some of the most common output metrics just to compare them and see how they worked uh, for my project. So I added the MAE, mean absolute error, also the MSE, the mean squared error, and its percentile in the MAPE as well. The first thing that I did with the original data set was to execute the function of data analysis for regression. This tool um, enables me to configure the key elements of the model. So, for example, in the input wide range, I use the E column, PE, as the one column that is gonna represent the target variable. For the X range, I selected from the um, A to the D columns, and this is what's done until for the first 80% rows of the data set in order to configure my output from the function. I also selected the labels confidence level to the default value of 95%, and I also selected the residuals info to get as part of the output summary. With this configuration that I did for my Model 1, I got the summary output that you can see here, in where it generates the regression statistics for the training, and also the values of the coefficients that it generate for my model. And in the residual output, I can see like the observation, for each observation, the predicted PE, and the different residual compared with the actual PE. So I just took the output of the predicted PE and copied them in a new G column in order to identify and to calculate some values. For example, I calculate the absolute difference between the predicted P and the actual PD. Also, its squared error and the absolute percent error. I did this for the first 80% of the data that I used to train the model. And I also did this for a second model, in where I try to compare the performance of this one with a second model. Given that in Excel I didn't have many options to change the algorithm, I simply use a different set of features just to compare if something changed deeply. And then my guess was that maybe the AT variable, the ambient temperature, maybe could be not as important as the rest of the uh, features. So I decided to do a second model with just the second, third, and fourth column of the model. And I repeat the very same process in order to use the first 80% of the data set just to execute the model. And I got this summary output with this similar structure, where I also copied the residual output to a new column in the G column, and also calculated, these three metrics in order to generate my different output metrics. So comparing them at first, you can see that the coefficient of determination R square was, for the first model, 1.92, and for the model number 2, 1.80, more or less. So that was the first comparison that I did, to train the model, and then I use the rest of the data set, the 10% of the data set, to compare those two models. So I calculate and I copy for starting at the column number 7,654. I use the formula with the coefficients manually to put here, like but to predict the target variable for the 10% of the data set, using the formula that I put manually, given the coefficients for each one of the variables. So I did that for my two models, and I got different R2 squared value, in where obviously model 1 was better at performance than model 2. And then I decided to use the remaining 10% of the dataset, the final one, to not to train or validate, but to use the model for the final 10%. And then I didn't get any hard variation in model 1, but my final my final output metric was a coefficient of determination R squared of 1.92, more or less. So this is the exercise that I did for selecting an approach, um, defining an output metric, comparing two different models, in where the model number two had one less feature compared with the model number one, and then given that model one was better performing than the number two, I decided to use it for the final data set, the remaining 10% of the data, to predict um, some of the data set with a fixed validation set, and then I get this R square of 1.92. That was the approach that I follow.